Morning everyone, this is Sanvita from Department of Civil. Today I am going to explain about the Jacobian evaluation for coordinate transformation in multi-axis robotic systems. So coming to the topic, Jacobian evaluation for coordinate transformation in multi-axis robotic systems. So exploring the mathematical foundation that enables precise control and motion planning in modern robotics. Why Jacobian? Why Jacobian coordinates or why Jacobian transformation? So the Jacobian matrix serves as a crucial mathematical bridge that converts joint velocities into ineffective velocities, encompassing both linear and angular motion components. So this transformation is absolutely essential for achieving precise motion control, sophisticated path planning, and accurate velocity mapping in robotic arms across diverse applications. So not only to solving problems, but the concept of this topic is also very important for the precise control over things or precise path planning or the velocity accuracy or whatever it is. So anatomy of the Jacobian matrix. So coming to matrix dimensions, for an n-joint robot, the Jacobian is typically 6 into n, capturing the complete velocity space. And the second one is linear velocity mapping. Upper three rows map joint velocities to linear velocity components x, y, z of the end effector. And the third one is angular velocity mapping. Lower three rows map joint velocities to angular velocity components. Roll, pitch, yaw. So SCARA robot example is that the Jacobian for a selective compliance assembly robot arm shows rotation exclusively around the z-axis, reflecting its specialized planar motion with vertical compliance. So there's this and robot called SCARA. So here the Jacobian for this assembly robot arm, there's a robot arm of SCARA, and for that the Jacobian is exclusively around the z-axis, only exclusively around the z-axis. So it is reflecting the specialized planar motion with vertical components. And this has happened only due to the Jacobian anatomy of a matrix. Visualizing Jacobian, the space Jacobian concept. So each column of the Jacobian matrix corresponds to the spatial twist, a combination of a linear and angular velocity caused by applying a unit vector at a single joint while keeping all other joints fixed. So these columns are dynamic entities that continuously change with joint angles, representing in real time how each individual joint influences the overall effector motion in the workpiece. Joint 1 motion is that base rotation affects all downstream links. And joint 2 to 4 motion is intermediate joints create compound effects. An end effector result is a combined spatial twist at tool center point. For example, in a 5-joint articulated arm, the Jacobian columns transform continuously as joints move, reflecting the real-time kinematic relationships and enabling predictive motion control. So here you can see the picture, and this is a first joint, this is a second joint, and here is a base arm. So this first joint motion is the base rotation affects all downstream links, and the joint 2, joint 3, and joint 4 motions is of intermediate joints which create compound effects. So this second joint, third joint, and fourth joint which creates the compound effects. And the fifth joint, sixth joint helps in rotation. And first arm, second arm, third arm, forearm, fifth arm is helped in doing things with the hands. And here we will apply the force. And moving on, step-by-step calculation of a Jacobian for multi-axis robots. Okay, so assign DH frames, establish Deniwalt Heisenberg coordinate frames at each joint following standard conventions. So compute rotation matrices calculation rotation matrices and displacement vectors between consecutive frames, and deriving transformations. So you can build homogeneous transformation matrices for each link using DH parameters, and extracts screw accesses. So identify screw access and assemble Jacobian columns using matrix exponential, and assemble final matrix. Construct the complete Jacobian linking joint velocities to end effector velocity in base coordinates. So complexion, handling complexion inverse and pseudo inverse Jacobians. So direct matrix inversion is often mathematically impossible or numerically unstable for redundant manipulators or robots in singular configurations where degrees of freedom are temporarily lost. So the Moore-Penrose pseudo-inverse Jacobian provides an elegant solution for trajectory following and solving inverse kinematics problems in these challenging scenarios. Singularity challenges. Configurations where the Jacobian uses rank can cause control instability and unpredictable behavior. Tolerance thresholds. Implementing numerical tolerance zones around singular points prevents erratic motion. And trajectory feasibility. Path planning algorithms must verify reachability and avoid workspace boundaries. And moving on, real-time Jacobian computation advances. So matrix differential calculus. Novel mathematical methods dramatically reduce computational overhead for Jacobian sorry, online calculation. So real-time computation of both Jacobian and time derivatives for adaptive control loops, and hyper-redundant support enables control of robots with many degrees of freedom beyond traditional six-axis systems. So these computational advances facilitate truly adaptive control strategies in robots with floating pace, changing axis configurations, or variable kinematic structures. So modern innovations, machine learning, and vision-based Jacobian estimation. So coming to visiometer Jacobian fields represent a paradigm shift, inferring robot motion characteristics directly from the video streams without requiring explicit geometric or kinematic models of the system. So soft robots, control of compliant deformable manipulators that defeat traditional rigid body modeling approaches. And bio-inspired systems, so octopus-like arms and other biologically inspired mechanisms with continuously variable stiffnesses. And adaptable platforms, low-cost robotic systems that can learn and adapt without expensive sensing infrastructure. And this approach opens transformative possibilities for controlling robots beyond conventional rigid ink manipulators, democratizing access to advanced robotic control. And coming to practical considerations and challenges. The workforce development, significant skill gaps persistent in robot programming, Jacobian-based control theory, and system integration. And cost-effective solutions, modular robotics platforms and robotics as a service models lowers barriers to entry. Coming to safety systems, collaborative robot designs incorporate advanced force sensing and predictive collision avoidance. Coming to training programs, they can develop comprehensive education in kinematics and Jacobian appliances. And accessible platforms provide simulation tools that enable affordable hardware for learning. And safety standards implement ISO protocols for human-robot collaboration environments. So next topic, mastering Jacobians unlocks robotic precision and flexibility. So mathematical foundation is that Jacobian evaluation forms the essential backbone of all multi-axis robotic control systems. An integrated approach combining classical kinematics with modern computation and AI expands capabilities exponentially. So future innovation, deep understanding empowers breakthroughs in manufacturing, healthcare, exploration, and beyond. The convergence of rigorous mathematical foundations, real-time computational advances, and machine learning innovations positions Jacobian-based control at the forefront of robotic technology. As we push the boundaries of what robots can achieve, mastery of these coordinate transformation principles becomes increasingly critical for engineers and researchers driving the next generation of intelligent, adaptive, and precise robotical systems. Thank you.